welcome back, room. So today we're going to be stepping inside of the world of real analysis. Namely, we're going to be discussing the divergence of the harmonic series. But before we get into that, maybe let's take a look at this important lemma that we'll use along the way. And after we're finished with that, we'll get to the main course. Okay, so let's take a look at this lemma. Every convergent sequence is bounded. It's a classic lemma, and not too hard to prove. So let's just get into it. So let's suppose, proof, suppose some sequence a sub n converges, and let's say it converges to L, so convergence, okay, converges to L, okay. Well, what does that mean? Well, we have a nice epsilon n definition of convergence for a sequence to some value, and that is that, of course, we have to include the for all epsilon greater than 0. So then, for all epsilon greater than 0, there exists some natural number n, capital N, such that if n, or I should say, such that for all n greater than this capital N, we have the following holds. Maybe I should choose a better marker for this. Okay, so we have the following holds, and the idea here is that after a certain finite number, these values get as close as we want to one another, to this limit, as close to the limit as we want. So the idea here is then that we have the distance, essentially, between a sub n and L is less than epsilon. So this is for all epsilon greater than 0, right? So we can choose any value of n greater than n, and we can always find epsilon such that this holds. Okay? So let's see. So let's try to apply this in order to prove our lemma. So this is pretty nice, right? Because we almost have some condition that bounds our a sub n. Note that this is equivalent. So this is equivalent to saying that a sub n is in this open ball centered, in this case an open interval centered at L of radius epsilon. Okay, because if we write this as an inequality, we'll have a sub n is less than L plus epsilon, which is greater, but it's also greater than L minus epsilon. So that implies this here, because a sub n is then on this open interval L minus epsilon to L plus epsilon. So this is equivalent to this definition of the ball in 2 dimensions, in 1 dimension, I should say. Okay, so how is this helpful? Well, maybe we want to fix a value of epsilon here, right? Specifically because notice that epsilon varies here, so it would be nice if we could fix a value of epsilon, because this holds for all epsilon with n greater than n, right? So that's fine if we do that. So how could we go about this? Well, let's see. Perhaps if we choose epsilon equals 1, we get a nice bound for all of these terms. In particular, we'll have, so let's let epsilon equal 1, okay? Again, this holds for all epsilon, so this is an okay choice. Well, let's see. Maybe let's write it like this. So let epsilon equal 1. Then we have the absolute value of a sub n. Well, we can add a 0 in here, right? A sub n minus L, or parentheses, plus L. And, well, let's use the triangle inequality. This is less than or equal to the absolute value, a sub n minus L, plus absolute value of L. Okay? But notice that we're setting epsilon equal to 1, and by assumption our n is greater than or equal to n, capital N, so this is going to be strictly less than, well, epsilon, which is 1 plus absolute value of L. Namely, since L is fixed, we found a bound for all n greater than or equal to capital N. But now we have a remaining finite set of terms that come before that. So now consider not just the set of these finite number of terms, but the absolute value of those finite number of terms. And that's maybe to deal with like problems when we try to compute like the maximum of that set or the minimum. Note that, or the maximum in this case, because if we take the maximum only of that set, we have negative numbers. If we take the absolute value of negative numbers, even if those negative numbers are less than these very big positive numbers, those negative numbers could be more negative than the other numbers are positive. You get what I mean. So if we take their absolute value, then it doesn't quite work out. So to be careful, we need to take the set of all the absolute value of these finite number of terms. So consider the following set then, which is a sub 1, absolute value of a sub 1, absolute value of a sub 2, all the way to absolute value of a sub n minus 1, capital N minus 1. It's a finite number of terms. There are exactly n minus 1 of those terms. Okay, so now if we take the maximum of the set, again, that has to exist. Well, first of all, maybe to be more clear, we can take the supremum of the set, and it's not too hard to show that the supremum in this case is just the maximum of the set. And again, the supremum exists because this is a bounded, a non-empty bounded set in the real numbers, and the real numbers is complete, so it has to have a supremum. Okay, so I'm leaving out some of the details, but it should be clear. I said them though, so it's fine. So take what should we call it? Let's take K, capital K, be equal to the max. Let's call the set S the max of S. Okay, so that is i.e. K is greater than or equal to the absolute value. I'll write it like this, it's more clear. The absolute value of a sub n is less than or equal to K, capital K for all n strictly less than capital N. Okay, so but now we have these two things. We have a sub n for n greater than or equal to n, capital N is less than this bound, 1 plus absolute value of L. But here, for n less than a capital N, we have this bound, K. So surely, right, if we take the sum of these two bounds, both of those will be less than that. That's not too hard to show, right? If we just take the sum of these guys, well, sure, well then, of course, well, let's just write it like this. Perhaps, to be clear, we have a sub n. Let's just, well, maybe to be even more clear, if we add both of these, inequalities, right, we'll sum 2n is less than, well, 1 plus k plus absolute value of L, okay? But 2n is of course greater than absolute value of a sub n, okay? Again, this is true for all n now, right? And so this is going to be our bound. So this holds for all n. Okay? So intuitively that makes sense. If we have a certain number which is greater than a set of numbers and another number which is greater than another set of numbers, their sum is surely going to be greater than both. Perhaps to be even more clear, right? This is going to be strictly less than 1 plus capital K plus absolute value of L, because we're adding some positive value. Again, this is the maximum of a bunch of, maybe I should say greater than or equal to, right? of a bunch of absolute values, it'll be strictly greater, of a bunch of positive numbers. Similarly, this k is going to be strictly less than, well, k plus another arbitrary positive number, okay? And so, indeed, since both of these are less than this number, we can just say that a sub n is less than that number for all n. That number is greater than a sub n in both cases, and thus it's for all n. And so that completes the proof of this little lemma. So I'll just clear the board, and we'll get to the main course. See you then. Okay, so on the board I kind of wrote out what the harmonic series looks like. And so here's the nth partial sum. We have the sum from k goes from 1 to n of 1 over k, and as n tends to infinity, we eventually get this infinite sum, which is as follows: 1 plus 1/2 plus 1/3, etc. So now the idea here is to show that it diverges, is to bound this sequence, and it is indeed a sequence, below by some, in this case it's going to be an unbounded sequence. And then from there we want to show that that actually implies that that sequence is unbounded, and that Sn is unbounded, which will then imply, using the contrapositive of our previous lemma, that it cannot converge. Therefore it diverges. Okay? So that's the kind of map, the kind of blueprint of what we're going to be going through. So let's see what we can do. How would we bound this below by something? Well, let's see. Maybe let's get rid of these first few terms. My marker will work. My marker isn't very kind. Okay. Okay. How about this one? Nice. So, okay, let's kind of bound these terms below by something. Notice that all of these terms are less than or equal to 1/4. So if we just replace these, this is always going to be greater than or equal to 1/4 plus 1/4 plus 1/4 plus 1/4. Note that that's just equal to 1. Okay. And how about these terms? This is a bit more interesting, and that's how this is going to generalize further down the line. This was kind of just going to occur once, but now we have a general case, which is we'll discuss that in a second. Just note that 8 is a power of 2 cubed in particular, and it goes down to a number right before the previous power of 2 squared, which is 4. And so, well, what happens if we replace all of these guys with 1/8? Similar to how we did here, although this is different because there's exactly 4 of these, okay? Well, let's see what happens. So we'll have one, this is always going to be greater than or equal to, my marker is not cooperating. It's going to be greater than or equal to 1/8 plus 1/8 plus 1/8 plus 1/8, and that's 4 1/8, which is 1/2. Okay? So now we want to look at the general case, because, well, if we think about it, we'll eventually get down to, well, we'll have like, further down the line, we'll have plus 1/9 all the way to plus 1/16, which is 2 to the 4, this is 2 to the 3. And if we sum up all of these guys, it turns out there's 8 of these guys here. That's not too hard to see. We're actually going to prove that in the general case, that there's going to be exactly 2 to the n. If this is 1/2 to the n, there's exactly 2 to the n minus 1 of these terms. And so if you sum up all of them, the answer is actually just going to be 1/2 every time. This is equal to 1/2 as well. So here's the idea. If we take arbitrary 1/2 to the n, so we'll have like, this is going to be our format. We're going to have like 1/2 to the n minus 1 plus 1/2 to the n minus 1 plus 1 plus ... and we'll eventually get to the next power of 2, which is 2 to the n in this case. Okay, Well, let's write maybe 2 to the n as, in order to count these guys more easily, in an easier fashion, this is 2 to the n plus 2 to the n minus 1. And now what's nice, if we instead count all of these guys, excluding this term, indeed this term is going to be involved in another sum in its previous terms. So we're starting at 1, and we're going up all the way, plus 2, plus all the way to 2 to the n minus 1. Well, that's exactly 2 to the n minus 1 terms that we're summing, right? And so this equals 1/2. Okay? So now, since we have kind of the tools to continue, let's take a look at this partial sum of Sn, which is going to be S sub 2 to the m, to use different notation. Okay. So this is going to be like this all the way to some. So I'll just kind of write this out. 1 plus 1/2 plus dot 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 plus 1 over 2 to the m. Okay. Well, let's see. Maybe if we transpose what we have here, it could be more clear. So plus 1/3 plus 1/4. This is a special case, so we kind of want to make it clear that that's there. Plus dot 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 plus 1/8 plus dot 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 plus, again, m could be 3, so this is kind of, we're doing this a bit loosely, but we have the m. If m is just 3, then this is really easy to simplify. So let's suppose m is greater than 3. So this notation is a bit abusive, but it's fine. So what do we have then? Well, notice that starting at 1/8, we're using this funny trick where we make all of these terms 1/2. And 8 is just 2 cubed, as we mentioned. So now it suffices to just, since we're doing this for every power of 2 greater than or equal to 3, let's just count how many of those we're going through. And that's easy. We can just count the exponents of these guys. So we're going from 3 all the way to m. How I would do this is just, because I'm really bad at counting stuff, so I just try to make this a simpler problem, which is counting from 1 through m and subtracting off 2 terms. So that's m, so this is just m. So if we subtract off 2 terms, we go to 2 and then to 3, and that's what we want. So we'll just get that this is m minus 2 terms. Okay? And what does that mean, though? That means that there's going to be m minus 2 of these 1/2. After we note that this is going to be bounded below by our argument, this is always going to be less than or equal to, since this number, if we replace every number with that, again, this is, if we just look at the sequence 1/k, it's a decreasing sequence, right? And that's why that holds. Okay? So this is going to be less than, well, first let's replace this by 1, as we noted here, plus, and now there's m minus 2 1/2, so we just multiply that. And, well, if you kind of distribute this 2, this is just equal to 1 plus m over 2. And, well, we might as well just use m over 2. Okay. Because this is just, so this is the bound we're going to try to, again, this is really no different from 1 plus m over 2, it's just adding a 1. So we'll just focus on this guy, m over 2. Namely, if we take the extreme right and the left inequalities, we're going to have s to the m is greater than m over 2. That's going to be the key result we need. So I'm going to erase some of this stuff, and we'll try to finish this off. So let's assume by way of contradiction that s sub n is bounded. So intuitively, this should make S sub 2m unbounded, because it's bounded below by something that's unbounded, clearly. But let's just prove that rigorously. Well, if Sn is bounded, then it's pretty clear that any subsequence has to be bounded. Okay? So, that's very clear, right? So, then, well, S sub 2m is definitely a subsequence. Then, S sub 2m is bounded. So, by assumption, or by definition of being bounded, so for all m, the natural numbers, for all m in the natural numbers, we have, well, I should say, oh, maybe I should be careful here. So there exists a capital M, because this has to come before. This M is not dependent on which term we have. There exists M, let's just say in the natural numbers. It could be any number really, but in the natural numbers, because you can always find, using the Archimedean principle, we can always find a natural number greater than some real number. Such that for all n in the natural numbers, we have the absolute value of S sub 2m is, maybe I should say S sub n, to use different notation here. This was a specific value, but now S sub n ranges through all such m. Should make that clear. This is a subsequence ranging through all n. This is less than m, but also, and we can just ignore these absolute values since this is always positive, strictly positive, so we needn't worry about these absolute values, but this is always going to be bounded below by 0, of course. But also, S sub 2n is greater than n over 2. And so it's sandwiched between these two guys. So that means that n over 2 is less than m. Okay. But now m is fixed. So what's the contradiction here? Well, this is just equivalent to n is less than 2m, and this guy is also fixed. This is some fixed natural number, but so call this, or I'll just leave it like this. So, but I'm being a bit messy here. But there has to exist some, I'll just use capital N again for lack of better notation, some capital N in the natural numbers such that capital N is greater than 2n. Okay, why is that? Well, that's because that's by the Archimedean principle, right? We can always find such an n. Okay, but this supposedly held for all n, so this is actually just a contradiction, because this contradicts this inequality, which supposedly held for all n. And so what have we contradicted? We've contradicted the fact that Sn is bounded. Okay, thus Sn is unbounded, and now we're pretty much done, which implies Sn diverges. And that again is just follows from the contrapositive of the lemma we proved. So you can look back on that if you want. Well, that about does it for this video. In the next video, maybe we'll look at something called Abel's theorem briefly, because it actually, it's funny because it actually also proves the harmonic series diverges very quickly. So perhaps we'll look at that in the next video. Then after that, we'll look at like compact sets or something, because that's very interesting. So see you then.